Alright, so last time we left off with Newton's law of universal gravitation and his second law. So let's go ahead and write his second law, which is F equals mr double dot. Don't forget the arrows above the letters to denote a vector. And double dot, the dots actually lined up. And we're going to go ahead and just automatically connect them. So F equals mr double dot is equal to m, which is the same here, and then so that's m1 times m2 times g over r squared. But we're going to write m1 and m2 different, so we're going to do m1 and m2, where big M is the mass of the Earth and little m is the mass of our spacecraft. And all that times g, and that's all over r squared. But to make sure this is also vectorized, so we end up with a force vector, we're going to add a unit vector, which is a unitless value equivalent to our position vector, r arrow, or r with the arrow above it, over the magnitude of our position vector, which is the same as this r squared here. So we can take this one step further and say g r, or position vector, over r cubed. All right, so now to get the two-body equation out of this, all we have to do is, divide by m, our mass of our spacecraft. So that will be r double dot, always forget the arrow, is equal to mg r cubed times position vector. That is the restricted two-body equation. So we can go ahead and make this look even cleaner by saying that this is equal to negative mu, like so. So this mu is equal to the mass of the Earth times the gravitational parameter. Now you can replace this mass of the Earth with any mass, such as the Sun, Mars, Venus, Moon, etc. And the reason we do this is so we don't have to write out this all the time. We don't want to have to write out the mass of the Earth and the gravitational parameter when we're doing math, because being that these are constant, mu is constant, so we can use one number instead of two. All right. So let me just go ahead and write gravitational parameter. All right. So now that we've got our equation, we're going to try and solve the two-body problem. So to do that, let's go ahead and bring everything over to one side. So r double dot plus mu r position vector over r cubed. And we're going to say that is equal to 0. All right. Now, before we can solve this, we need to introduce two other parameters, which are constants of motion, and these are involved with our conservation law, so the conservation of energy and the conservation of momentum. So we'll start with the conservation of energy. All right, so the conservation of energy, energy is never created or destroyed, it just changes forms. And assuming gravity is our only force acting on the spacecraft, our energy, or our mechanical energy, more specifically, is only going to change between potential and kinetic. So if you've taken a basic physics class, you should know the equation for kinetic and potential energy. but the potential energy here is a little bit different. So our orbital potential energy is actually equal to mu times mass over r, which is the distance between the center of the Earth and the spacecraft. Now, our kinetic energy is just like from your physics class, which is 1/2 mass of the spacecraft times the velocity squared. And we're going to go ahead and say this is equal to E. So E is equal to our kinetic energy plus our potential energy. And being that our potential energy is going to be facing down towards the Earth, it's going to have the minus sign. The constant of motion that we want to work with here does not depend on the spacecraft's mass. So we can go ahead and divide everything by a little m to get epsilon, which is just E divided by m, equal to v squared over 2, so our orbital velocity, minus mu over r. So our specific orbital potential energy and our specific orbital kinetic energy. Now, what's great about this is you can use the specific orbital energy to find your velocity at every point in the orbit, or your position if you know the velocity. The specific orbital energy is going to be constant no matter where you are within the orbit. So if you draw a quick orbit, so here's Earth. If you're here, it's going to be the same as if you are here. There is another way to find your specific orbital energy, and that is by, so that is equal to negative mu over 2a. And we will derive that in a separate video. So, and I'm just gonna write out how you can find your velocity at any point in the orbit, assuming you know the energy. V squared over 2 minus mu over r equal to negative mu over 2a, which a is our semi-major axis. And you can find v is equal to square root of 2 times mu over r plus orbital energy. All right, so the other constant of motion we need to know is the specific orbital angular momentum, which we will represent by h. So h, with a vector, because this is a vector, unlike our energy, which is just a magnitude. Once again, this does not depend on your mass. Instead, this depends on just your position vector, which is r with the arrow above it, crossed with v. Now this x, I know to some people the x means multiply, but here it does not. It means cross product. And I'm not going to cover what a cross product is here, but we'll work an example later and you should be able to see it there. This h, and the reason this is a vector is because the specific orbital angular momentum vector is always going to be pointing perpendicular to both your position and velocity vector. So if we wanted to see this, we could draw like a 3D Cartesian plane. So you've got your position vector and your velocity vector. It doesn't look like a 90 degree, but that's 90 degrees in 3D. And then coming straight up, you've got h. So it follows the right-hand rule. I'm really bad at doing that, but my thumb would be the angular momentum vector. This is r and this is v. That should be more straight. Or we can draw this on an orbit. And let's say the center is here. So R, this is R, and then V will be perpendicular to that. And H would be coming straight out of the board then, or straight down, depending on if these are flipped or not, or if the V is flipped or not. So here, look, oh yeah, there you go, right hand rule. So we can gather from this that the R and V vectors define our orbital plane for a two-body orbit. And therefore, H is always going to be in the same locate, or fixed in space, essentially. All right, so now that we know those, we can go on and solve the two-body problem, which we'll do in the next video.